Namaskar and welcome back to this discussion on concrete engineering and technology, where we are studying fundamentals of concrete, proportioning of concrete mixes, stages in concrete construction, special concretes and so on. And continuing with our discussion on proportioning of concrete mixes, what we will do today is to focus on proportioning of simple concrete mixes, that is only those which have water, cement, fine aggregate and coarse aggregate. The mixes which have other ingredients like chemical admixtures or mineral admixtures, we will take up for discussion subsequently. Now, before we get started with our discussion on actually proportioning concrete mixes, let us quickly go over some of the things that we have done in the past. We have gone through the properties of the basic ingredients of concrete, that is cement, water, fine aggregate and coarse aggregate. We have gone over concrete properties like workability, which is typically measured in terms of slump, and compressive strength. We have gone through some of these very important ideas which govern our proportioning exercise, that is the water slump relationship, the characteristic and target strengths for proportioning concrete mixes, water cement ratio versus strength relationship, and the importance of S by A. Now, this is the final relationship which we had agreed on slump and unit water content. We had said that for a given set of materials and their properties, the variation may be taken to be a single straight line, that is, there is a particular variation for slump and unit water content depending on the actual materials being used in a project. Similarly, when we talked about the characteristic strength versus target mean strength for proportioning concrete mixes, we had said that characteristic strength is what a designer uses to design structural elements like beams, columns and so on, and the assumption there he makes is that not more than 5% of the values that are obtained in the concrete actually will be lower than this value. And the concrete proportioning has to be carried out using what was called the target proportioning strength of concrete or the target strength of concrete, which is basically the strength of the mix that we use, and that has to be determined in a manner that the characteristic strength criteria is satisfied. We had said that if 5% of the samples are allowed to fall below the characteristic strength and the actual strength of the mix is assumed to be normally distributed, then the mean strength may be taken to be characteristic strength plus 1.65 times standard deviation, with the factor 1.65 coming from the fact that we are allowing 5% of the samples to fall below characteristic strength. Thus, in other words, if a concrete mix is designed with a target strength which is the mean, then it will satisfy the design characteristic strength. Carrying on from our previous discussion, we had said that much like the relationship between slump and the unit water content, the relationship between strength and the water cement ratio can be taken to be a simple straight line in a manner that as the water cement ratio increases, the strength decreases, and each point on the line really represents the mean of the normal distribution of strengths that we get when we test a large number of concrete cubes or concrete samples at a given water cement ratio. Then discussing the S by A or the importance of the sand component or the percentage of sand in the total aggregates, that is the total inert material. We had said that normal concrete has a certain amount of fines as a proportion of the total inert content. If we go to no fines concrete, we have basically said that S by A will be a very small value. It may be 0 in the extreme case, in which case we are talking of no fines concrete. Similarly, on the other extreme, we have mortar, where S by A is virtually 1, that is no coarse aggregate in the system. In other words, S by A is used to control the amount of mortar in the concrete mix, and how much do we need, how much of mortar do we need in the concrete mix is determined by the type of coarse aggregate, the size of the coarse aggregate, its properties, particle size distribution and so on. Basically, what our requirement is that the mortar should be able to fill all the voids within the coarse aggregates, and not only that, since in concrete the coarse aggregates are not really in contact with each other, we have to provide additional amount of mortar, so that concrete comes out as a homogeneous mix in a particular volume. As far as air content is concerned, we have talked about it, and we have said that air is either entrained or entrapped, depending on whether we are talking of air entrained concrete or non air entrained concrete. And in the case of entrained air, that part is intentionally put in place, and particles are very fine and uniformly distributed within concrete, whereas entrapped air is present unintentionally and is generally much larger in size as far as the individual air particles or pockets is concerned. Now, from this recapitulation, we move on to our exercise of proportioning concrete mixes, where we have to make sure that the concrete satisfies the requirements in the fresh state, which could show in the fresh state, which could be workability and so on, and in the hardened state, which is strength. Please recall that in the fresh state, concrete shows behavior which is similar to that of a fluid, and it can be pumped, it acquires the shape of the mold in which it is poured and offers very little resistance to deformation. However, as the hydration continues and the concrete becomes more and more solid, in the hardened state, the solid material, that is the concrete, has substantial compressive strength. So, we have to make sure that both these properties are satisfied as far as the proportioning is concerned. So, functionally concrete should satisfy laid down criteria for the fresh state, that is, it should have the required workability, air content and so on. In the hardened state, it should have adequate strength, and other than that, there could be requirements in terms of durability. For example, it could be in terms of restrictions on parameters such as the water cement ratio, the cement content, or there could be other requirements, like somebody may say that the temperature rise that occurs during the hydration process should not exceed a certain number. The setting time of concrete should not be less than or more than a certain number. If I want to explain, let us take the example of setting time once again. In the case that concrete is being used for a repair job, there we would expect the concrete to set faster than a normal concrete, and therefore, there can be a requirement that the setting time of concrete should not be more than a certain number or a certain time period. Similarly, in certain cases where we want to prevent the formation of a cold joint, that is, we pour some concrete, there is something needs to be done at site before the concrete is poured again. We want to prevent the formation of that cold joint, we may say that the concrete is not allowed to set, in which case the specification will be that the setting time of concrete should be at least a certain number. Please remember that the setting time of concrete is not really the same as the setting time of cement. Setting time of concrete is determined in a certain different way, which we have talked about earlier when we were talking about the properties of concrete. Remember and recall that to determine the setting time of concrete, we removed the coarse aggregates and used mortar and used the principle of penetration resistance to determine that property. Now, the objective therefore of the proportioning exercise is to find a suitable combination of the relative amounts of sand, water, coarse aggregate and cement, so that concrete has the required properties in the fresh and hardened states, and it meets the durability and any other requirements that may be imposed on the structure depending on the type of the structure or the environment. In marine environments, certain codes require certain maximum water cement ratios. They may impose restrictions on certain minimum cement content. In certain cases, there may be a restriction on the maximum amount of cement used, and so on. So, all those criteria have to be met as far as the concrete that we design. Now, look at this picture once again, which is what this course began with. Concrete as a multi-phase material composite, as a multi-phase composite, looks like this. This is a slice of normal concrete. Modeling this, we want to go to this kind of a picture, where we say that all these aggregates and sand and cement, everything is spherical, suspended in a solution of water and suspended in water, and so on. And if we lump all these things together, we have so much of gravel, so much of sand, so much of cement and water. That is what we have talked about all this while. That is what we have talked about all this while. And now, the challenge is to find out the relative amounts of each of these ingredients. Now, let us look at this picture once again, and this is what sand and coarse aggregate and fine aggregate everything looks like. Now, if I was to just run a model which says that I have brought all my coarse aggregate together at one place, and it is something like this. All my fine aggregate is brought here, all my cement is brought here, all the water is brought here, and all this void space at different places is taken to the air. So, this is really what proportioning the concrete really boils down to. So, let us take a look at this animation once again. So, you can see how the animation works, or what really is the basis for this picture, which is a very important picture as far as proportioning is concerned. It really tells us that this is the amount of coarse aggregate that we are using, this is the amount of fine aggregate that we are using, this is the cement that we are using, this is the water and air. Of course, when we do the proportioning, we have a certain procedure, we have follow certain steps to make sure that this happens. Another important picture that we have as far as the proportioning exercise is concerned is this story of the pitcher and the crow. The importance of this picture is the following. In this picture, what we have heard all this while is that there is a fixed volume of the pitcher. That is, the volume of this pitcher is fixed, and the proportioning exercise as far as concrete is concerned is really to find out the quantities of the different constituents, that is sand, cement, coarse aggregate, such that the pitcher is filled. That is, the sum of the volumes of all the ingredients is equal to the volume of the pitcher, and the properties of the concrete satisfy the required conditions. We cannot just have water there, we cannot just have coarse aggregate there. The combination of the different materials should be such that when they are held together, then the concrete satisfies the properties, and also the sum of the volumes of the ingredients is the same as the volume of the pitcher. Now, to make things easier for us, what we do is we work with a 1 cubic meter or 1000 liter pitcher and determine the quantities in kilograms. We have to determine the quantities in kilograms because determining the absolute volume of coarse aggregates or fine aggregates or cement is a very, very difficult job. It is much easier to weigh those ingredients and find out the kgs per cubic meter of each of these ingredients. Having said that, we also need to know their specific gravities, so that we can convert them. We can convert the mass to the absolute volume, and then make sure that the sum of the absolute volumes is the volume of the pitcher, and for sake of convenience, we take the volume to be a cubic meter or 1000 liters. So, this is what we are trying to do. We are trying to find out how much of each of these constituent materials is, such that the quantities expressed in kgs per cubic meter, except for air of course, but the exercise is quite to an extent volumetric. Now, what is the fundamental basis of determining the relative proportions of cement, water, fine aggregate, coarse aggregate? The fundamental assumptions or the basis is that for a given concrete mix, the slump is determined primarily by the unit water content, and that is what we were talking about when we talked of and we discussed in great detail the unit water content versus slump relationship. We said that slump or workability of a concrete is determined primarily by the unit water content, and that depends also on the type of materials being used. Then the strength is determined primarily by the water cement ratio. So, with these two assumptions, we actually get started and carry out the exercise of proportioning concrete mixes. What it means in numerical terms, as an example, is shown here. If we have 3 mixes 1, 2 and 3 and they have water content, these values are in kgs per cubic meter and water cement ratio is in percentage, the strength is in MPa and the slump is in millimeters. Now, if 180, 200 and 200, these are the water contents that we have for these 3 mixes, and the cement content is shown to be 360, 360 and 400 as given here. The water cement ratio for these mixes turns out to be 180 by 360, which is 50, 200 by 360, which is 55 and 200 by 400, which is 500, which is 50 once again. Now, the assertion is that a water cement ratio of 50% gives a strength of 35 MPa, and 180 kgs of water, a unit content of 180 kgs of water per cubic meter of concrete gives a slump of 80 mm. Then what we are stating is that the strength in mix 1 and mix 3 is the same as the water cement ratio is the same. So, water cement ratio in mix 1 is 180 upon 360, which is 50%, and in mix 3 it is 200 upon 400, both are 50%, and therefore, the strength values is the same 35 MPa. However, since the water content in mix 3 is higher than the water content in mix 1, the slump in mix 3 is higher. It is, let us say, 100 mm compared to the 80 mm that we had in mix 1. However, continuing from that argument, the slump in mix 2 and mix 3 is the same as the water content is the same. So, if we look at mix 2 and mix 3, since the water content is the same, that is 200, both these mixes will have a slump of 100 mm. Of course, these values of 100 mm and 50% and 35 MPa of strength, these are illustrative values, and please do not attach more importance to them than that. The principle being emphasized is that the slump is determined primarily by the unit water content and the strength is determined primarily by the water cement ratio. Now, let us try to take a look at governing considerations once again. We know that the unit water content slump relationship is linear and the lines could depend on aggregate properties and so on. Similarly, the water cement ratio and compressive strength relationship is again linear, and these lines also depend on factors like the age, the type of cement, the amount of cement and so on. Then a balance between the amounts of fine aggregate and the coarse aggregate is required for good concrete. That is, it should have just the right amount of mortar, and that is expressed through the S by A, which varies with the shape and size of the coarse aggregate, the fineness modulus of the fine aggregate, amount of cement in the mix and so on. You will recall that fineness modulus is a single parameter which is representative of the particle size distribution of the aggregate, whether it is fine aggregate or it is coarse aggregate. And we have durability requirements or any other requirements that may be imposed on the concrete mix in terms of a water cement ratio, which can be said that it should not exceed 50% or 45%. Similarly, there can be a restriction on the use of cement to be at least 400 kgs per cubic meter or at most 350 kgs per cubic meter and so on. So, with these governing considerations, we proceed to carry out the proportioning of concrete mixes, that is determining the amounts of water, cement, fine aggregate and coarse aggregate in a concrete mix. Now, what is the required input? Based on the air content that we need in the concrete, the slump unit water content relationship, which has to be either given or determined for a given set of materials and their properties. The compressive strength versus water cement ratio relationship. That again has to be either given or it should be determined in a certain range depending on the properties of the materials being used. The required S by A or the mortar content, which will determine the mortar volume and requires other parameters such as the particle size distribution of fine and coarse aggregate, fineness modulus and so on, and the material properties per se, that is specific gravity of cement, fine aggregate and coarse aggregate. If we have all this input, then we can proceed to proportion the concrete mix, as we shall see. As far as the air content in fresh concrete is concerned, that is the first step. So, given that we are trying to work with 1000 liters, that is the pitcher volume, the air content in fresh concrete is an input and is assumed to be known for the present, and what we are left with is to fix the remaining volume in the 1000 liters. Now, we come to the unit water content and slump requirement. Be told, we have to know the required slump. What is the slump that we need for the particular concrete, depending on parameters such as the details of the structure. If the structure, for example, has a lot of dense reinforcement, we may need that the concrete should have higher slump. If the concrete has to be placed in a structure which has very nominal amount of reinforcement, we may be able to make do with a slump which is very small. So, somebody has to tell us what is the required slump, and once we have that, this is the required slump that we are working with. We can determine the unit water content based on the slump unit water content relationship in this manner. So, if we know this slump here, we know that this is the unit water content that we know. This is the unit water content that we need. In other words, what we have achieved now is that we knew the air content earlier. Now, we also know the unit water content, and for water, the density being 1, we can convert from the mass to the volume with relative ease, and we have fixed the amount of water in volumetric terms. The remaining part of the picture is still to be determined, how much cement will go into it, how much fine aggregate and how much coarse aggregate, that still has to be carried out. For that, we now need to determine the cement content. And how do we determine cement content? We know the strength versus water cement ratio relationship. We need to calculate the target strength from the characteristic strength, the likely standard deviation and so on. This is what we have done in a previous exercise, and we know how to work with it. That is, given a target strength, that is, given a characteristic strength and the standard deviation, we can find out the target strength. And once we know the target strength, then we know how much is the required water cement ratio based on this graph x y or this variation that we have assumed, and we know what is the water cement ratio that we need. And once we know the water cement ratio, we can calculate the cement content, because the water is already known to us from the previous discussion on slump. So, we know the water content, we know the water cement ratio, and therefore, we know the cement content. Now, please remember that water cement ratio is by mass, water cement ratio is not by volume, and therefore, once we get the amount of cement, that is the cement content, we really get the mass of the cement that we need in a cubic meter of concrete. And in order to convert this mass to the volume, we need to know the specific gravity of the cement. So, going back to that model where we are trying to proportion the 1000 liters, which is the absolute volume of the pitcher. We already knew the air content, we knew the water content from the slump water content relationship, and we now know the cement content from the water cement ratio relationship with strength. The remaining part is still to be fixed, and that is the part which is the inert material. We should remember that this cement content that we determined in this example was coming from the strength and water cement ratio alone. It is possible that other criteria such as durability or the heat of hydration may govern the cement content. So, it may be stated that this cement content that we get from strength may be higher or lower than that permitted or required from durability considerations. In fact, that holds for the water cement ratio itself. So, we will work with those examples as we go along in this discussion. Now, as far as the determination of fine and coarse aggregate is concerned, what is the crux of the problem is that the remaining volume needs to be divided between the fine and the coarse aggregates. More sand means more mortar content in the concrete or in the matrix, and less sand means less mortar. What governs the mortar demand? The mortar amount or the volume of mortar should be such that it is able to cover all the coarse aggregate, and sand to aggregate ratio, that is S by A, what we talked about, is used or can be used to control the sand volume in the concrete depending on the mortar amount that we need. The value of S by A needs to be adjusted depending on the size, the type of aggregates. For smaller coarse aggregates, a higher S by A is needed, because if the coarse aggregate is smaller, the surface area of those coarser aggregates that needs to be covered with mortar is higher, and therefore, the volume of mortar is higher. This implies that we need to work with a higher S by A. Arguing completely the other side, if the coarse aggregate size becomes larger, the area of the coarse aggregates that needs to be coated with mortar is lower, and therefore, we need a smaller amount of mortar in the concrete mix, and in order to get a smaller amount of mortar, we need a smaller S by A. So, with this understanding, we have now, once the sand content is known, the coarse aggregate content is automatically fixed. We could convert from the volumetric considerations to the respective mass using specific gravity of coarse aggregates and fine aggregates. What we have done is that we started with 1000 liters of volume, which we need to proportion. First of all, we fixed air, which was a volumetric measure. Then we fixed water, which was a volumetric measure. Then we determined the cement by weight, converted it to volume, and as far as the remaining part of the picture is concerned, we divided the sand and coarse aggregate using S by A, and we found the fine aggregate content, and the remaining part was the coarse aggregate. So, this in principle defines the process or the procedure that we follow for proportioning simple concrete mixes. The basic steps once again are to know the air content, to know the water content for the required workability. The required workability itself is related to the kind of construction that we need to do, whether it is a beam or a column with congested reinforcement, not so congested reinforcement, a plain concrete construction, for example, in a dam, or a very lightly reinforced construction, which may be, for example, in a pavement, and so on. Then we determine the cement content using the water cement ratio versus strength relationship. The required strength itself is determined from the characteristic strength and the standard deviation that we may have. As far as the inert content or the volume of the inert materials is concerned, that is determined using the S by A concept. We find the sand content within the total aggregate volume, and then the coarse aggregate content automatically gets fixed. So, this in a nutshell is the exercise of proportioning basic concrete mixes. We start with a target slump and air content, compressive strength. Since the determination of compressive strength takes time, only the former are discussed in this, are taken up for discussion here. We work with slump and air content. We assume that the compressive strength issue will be taken care of in due course, and if a requirement is there to change the required water cement ratio, it can always be implemented. Proportioning can in principle be carried out once the air content, the unit water content and the water cement ratio and the S by A, these 4 parameters 1, 2, 3 and 4. If these 4 parameters are known, then the proportioning can be carried out almost mechanically, except of course, to determine each of these parameters, there is a lot of effort that needs to be done. There is a lot of data that needs to be generated. There is a lot of understanding that we must have of concrete engineering. Having achieved the proportions as described here, we will possibly need to make minor adjustments, which we will also see in a subsequent discussion in the concrete proportion that we determine. Now, let us take up an example. A table of the type which is given here is often the starting point, where it is stated that for a given size of coarse aggregate, let us say 20 mm or 40 mm, whether the concrete is non-air entrained or air entrained, the air content may be taken to be 2% or 1.2%, it may be taken to be 6%, 4.5%, whatever it is. The water content that may be normally required would be about say 185 kgs or 165 kgs. The S by A may be 45, 36 and so on. So, these are values which are typically given for a certain condition, maybe for a water cement ratio of 55%, a slump of 8 centimeters, with the sand being used having a fineness modulus of 2.8. Now, as far as these values are concerned, the air and the S by A is by volume and water is by weight, that is, it is given in kgs per cubic meter. And of course, as far as AE concrete is concerned, we may need to use chemical admixtures in order to make sure that a certain amount of air gets entrained in the system. As far as this table is concerned, I would like to draw your attention only to the fact that once the size of the coarse aggregate increases, the amount of water required for that same workability, which we are working for example, at 8 centimeters, is much lower. That is something which you should keep at the back of your mind and then start proportioning the concrete mix. For a certain set of conditions, this is the starting point, that is the reference which can be used to initiate proportioning exercise. We need to adjust this particular values for the aggregate type, the cement type and so on and so forth. Now, in the discussion so far, we have gone through a procedure for proportioning a normal concrete mix and learned what kind of information or input data is required to be able to carry out that exercise. We are now ready really to work with numbers and see how this process actually yields a design mix. We are now ready to work with numbers and try to see how this algorithm or this process works and gives us a mix design. Let us take the examples of let us take the required basic input for a illustrative example. We say that we need an air content of 5%, a slump of 80 mm. We have a characteristic strength of 25 MPa. Expected standard deviation in strength is 3 MPa. The S by A for given aggregate characteristics, that is the particle size distribution of the coarse aggregates and the fineness modulus of the fine aggregate. The required S by A or n S by A with which we would like to start our iteration is 0.36, and the material properties in terms of specific gravity of cement, fine aggregate and coarse aggregate are known to be 3.1, 2.61 and 2.63. So, with this basic data, we are now going to start the exercise of proportioning the concrete mix. Other input that will be required is from the slump unit water content relationship. We need to have the water content, and let us say that for the required slump, the water content is found to be 160 kgs per cubic meter. Similarly, given that the characteristic strength is 25 MPa and we knew, and we are following a model where the target compressive strength is determined using the characteristic strength plus 1.65 times the standard deviation, we get 29.95 or 30 MPa as the target strength. And from the strength water cement ratio relationship, the required water cement ratio for this concrete is, let us say, 50%. So, that is the data which we have to have in addition to the basic requirement that was in the previous slide, and with this information we are now going to embark upon the process of determining the relative volumes of air, water, cement, fine aggregate and coarse aggregate as we have been doing. Now, the first thing that is given to us is that there is 50 liters of air, given that the air content is 5% by volume, 1000 liters is the volume of the pitcher, we have 50 liters of air in the system. That is, we know that there is 50% or we know that there is 50 liters of air in the concrete. Continuing from there, we know in the second step that we need 160 liters or 160 kgs per cubic meter of water from the unit water content versus slump relationship, and for the required slump, that is, we have the air content fixed and the water content known. So, we have fixed 160 liters of water per cubic meter of concrete. Continuing from that point, we go to the third step, where we are now also given that the water cement ratio is 50% by mass, which means that given the fact that we are using 160 kgs of water, we have 320 kgs of cement. Further, since the specific gravity of cement is known to be 3.1, the volume, that is the absolute volume of the cement that we have, is 320 divided by 3.1, which is 103.2 liters. I am leaving it to you as an exercise to convince yourself that the amount of cement given in kgs divided by the specific gravity will straight away give you liters of the material. That I am leaving out, and what we are getting now from here is that we have 50 liters of air, 160 liters of water and 103.2 liters of cement in the system or in that particular concrete. What is left is this volume, which means that the remaining volume, that is the sum of the fine and the coarse aggregate, which is 1000 liters, that is what is the total volume. This is the volume of the air, volume of water, volume of cement. The total volume for inert material left to us is 686.8 liters, and this has to be proportioned in the fine aggregate and coarse aggregate. Given that the S by A is 0.36, the volume of the fine aggregate is 0.36 multiplied by this volume that we have for all the inert material, and we get the volume of fine aggregate to be 247.2, and the volume of coarse aggregate can be either determined by saying that okay, that is the remaining volume, that is 1 minus 0.36 is 0.64 times the total volume, which is this amount of volume for coarse aggregate, or we could simply say that this was the total amount of inert material available to us, and out of that 247.2 was the sand content, and therefore, 686 if we, and therefore, 439.6 is the volume of coarse aggregate. Pictorially represented, this is what we have achieved. We have the concrete which will have 5% of air, that is 50 liters of air, 160 kgs per cubic meter of water, 103.2 liters of cement, 247.2 liters of fine aggregate, and 439.6 of coarse aggregate. That is the absolute volumes of the different ingredients as far as the concrete is concerned. Now, we can convert all this, which was by volume, to mass. That is, we multiply this by the specific gravity here, and we get 645 kgs per cubic meter of fine aggregate, and similarly, if we multiply the specific gravity of coarse aggregate, which was supposed to be 2.63, we get 1178 kgs per gram, we get 1178 kgs per cubic meter of coarse aggregate. We could convert all these calculations that we have done to a final figure, which will give us 50 liters of air, 160 liters of water, 103.2 liters of cement, 247.2 liters of fine aggregate, 439.6 liters of coarse aggregate. We can convert all this volumetrics to the mass and say that the concrete will have 50 liters of air, 160 kgs per cubic meter of water, 320 kgs per cubic meter of cement, 645 kgs per cubic meter of fine aggregate, and 1178 kgs of coarse aggregate per cubic meter. What we have really done is converted these volumes to this mass using specific gravity. And in the initial part, we went from here to here, that is from the mass of cement that we determined. For a given water cement ratio, we determined the volume of cement again using the specific gravity. So, that is what has been the outcome for the day, where we have tried to understand the algorithm to carry out the proportioning of concrete mixes, and we have also gone through a numerical example of how this procedure is actually implemented. Now, before we close the discussion, we should remember that we set out with the belief that the proportions that we decide will yield that the concrete that we make will have a desired set of properties in terms of slump, air and strength, but that may not always happen. For such cases, we need to revise the mixed proportions, and just how we can do that, we will see the next time. However, having said that, let us go back to recapitulate a few things and do some work on our own. Indian codes, for example, IS 456-2000 talk in terms of a nominal mix and a design mix. I would like you to find out more about these. What is a nominal mix? What we have done today is a procedure for designing concrete mixes. I would like you to study specifications of concrete which lay down the requirements of a maximum water cement ratio, minimum cement content or a maximum cement content, and better understand what are the kind of conditions or applications of concrete construction where such restrictions are imposed on the concrete in terms of its constituent materials. How is the workability requirement determined for a reinforced concrete construction? I did mention that if we have congested reinforcement, we would need a concrete with a higher slump, but that statement needs to be quantified, and different specifications in the world help us determine this actual slump requirement for a given level of density of the reinforcement in the concrete construction, which is measured in terms of kgs of steel per cubic meter of a concrete. We would like you also to study a little bit more about some other methods of proportioning of a concrete mix than we have done here, which was a simple method based principally on volumetrics, though we converted the volumetrics to a mass based discussion at the end. And with that, we come to an end for today's discussion. Thank you.